Okay. Assalamualaikum warahmatullahi wabarakatuh and good afternoon. Can all of you hear me?
Salam Doktor, yes.
Okay, okay,
Boleh dengar.
okay, okay. So before we begin, please sign in your attendance. Okay,
Uh,
so
Alaikum
today,
salam, doctor.
salam.
Good afternoon. But your screen is not clear for us, doctor.
Sorry, do you mean you cannot see my power slide, PowerPoint slide?
Yes, yes.
Yes.
Huh? Okay, okay, okay. I have share. Okay, okay. I will try again. Okay, is it better now?
Yes, it's okay now.
Okay. Okay. So for today, okay, I will discuss on the soil dynamics. Okay. Okay. For my parts, there will be 5 subchapter. Okay, which is I will discuss on the introduction of the soil dynamic. Okay. Uh, next 2 weeks, because next week will be Dr. Programli class. Okay. So next 2 weeks, okay, I will discuss on the what we call as on the uh, shallow foundations, okay, under under dynamic loads, okay, and then I will discuss on lateral stress, okay, under dynamic loads loading view, okay. For the next sub chapter will be on uh, deep foundations, okay, due to the effect of the machine vibrated machines, okay. And the last one will be on brace cut, okay. However, for the brace cut, it will not related to soil dynamic or dynamic loading, okay. So there will be 5 subchapter, okay. So for the assessment, okay, for my parts, okay, consists of 40 marks, okay. So there will be an assignment, project, and take-home test, okay. So there will be no final exam for this subject, okay, both for SKAB 4733 and also for MKAG 1033, okay. So my name is Ahmad Safwan Irashid, okay. Um, Actually, I'm the associate chair, okay, which is take uh, in charge for the facility, okay. Yeah, Prof. Khairul is the chair, and then I am the associate chair, okay. So with this, I in charge on all the facility in SKA. Okay. So for today discussion, okay, I will give a brief introduction on the soil dynamics. Okay. So later on we may discuss on the soil structure interaction. Okay. And then I will touch on wave propagation in soil. Okay. And then I will conclude with the method to overcome or to reduce the effect from the vibrations, okay, especially from the earthquake effect. Okay. So in this particular subject, I will discuss only on the stabilization of ground for geotechnical structures. So we may discuss only on this subchapter for today. Okay. So hopefully it's not the class will be not more than 2 hours. Okay. So as we know, okay, all the civil engineering structure, okay, will be built or designed on a ground, okay, starting from the hilly part, okay, for example, for natural slope, okay, so we may, what we call as, we may design for the natural slope to make sure that the factor safety should less than 1.2, okay. So if we do any cutting, okay, so then we need to design the factor safety should be greater than 1.5, okay. And then for the embankment dam, okay, or to build a reservoir, water reservoir, so we need to contain the water by using a dam, okay. So this example of embankment dam, not a concrete dam, okay. So from this kind of type of dam, so we need to determine what will be the seepage, okay, the rate of seepage, okay, uh, which is to be calculated in order to make sure that the dam is stable. And then if we move to the building construction, so the most important thing is to calculate for the bearing capacity of the foundation, okay, where all the load will be transmitted to the slab, from slab to the beam to the column, and to the substructure, and then transmit to the, what we call, to the ground, okay. So for the building foundations, either we use shallow foundations, or we may need to use deep foundations. Okay. So for the in order to build for example a basement, okay, or to build a trench, okay. So we need to support the hole or the excavation by using brace cut system. Okay, so this is the brace cut. Okay, so where we install what we call it, for example, a sheet pile, and then we use a bracing system, okay, to avoid for any collapse, okay, from the lateral, from the side of the soil. Okay, so for the tunnel, okay, we need to identify what will be the stress that be induced by the tunnel, okay. So we need to have identify the value of the stress. Okay, I guess we may learn during the tunnel uh, elective class. Okay, so when we want to construct a highway or a train track, so we need to have or to construct an embankment. Okay, so the stability of the embankment in terms of the slope and also the foundation should be calculated, okay, to make sure that the embankment is sufficient to sustain the load from the car, okay, or from any vehicle, and also to make sure that the foundation could sustain the load from the embankment as well. Okay. Then when we want to construct any, for example, a building or a harbor or port nearby the seaside, okay, so we need to understand the characteristic of soft soil, okay, where we need to get all the information, especially on the compressibility of the soft soil, okay. So then we can start to do any treatment, okay, in order to strengthen up the soil of uh, below the ground, okay. The lastly, okay, when we want to design for any offshore foundation, which is the foundation is located on the ground, okay, so we need to understand the characteristic of the seabed uh, properties, okay. So meaning that all the civil engineer begin with geotechnical engineering, okay. So you should be proud to become a geotechnical engineer in future, or now you have already become this geotechnical engineer for the master student, okay. Okay. So this is a typical geotechnical project. Okay. Where we if we are provided with land and to construct something on any structure on the top of the ground. Okay. So the most important thing as a geotechnical engineer, so we need to get all the related information, especially on the soil properties. Okay. So what should we need? For example, strength, stiffness, and also consolidations. Okay. So in order to get all these informations, okay, either we carry out for site investigation at the site, okay, and then we bring all the sample, okay, either undisturbed or disturbed sample to the lab, okay. So bring to the lab and then conduct all the required tests, okay. So from there we gain all the soil properties, okay. So from the soil properties, okay, we can uh, carry out for the design, okay. So now, for example, if the problem is very complicated, so you cannot hear my voice. Hello?
Assalamualaikum Prof.
Salam, tak dengar? Can you
Ada
hear my voice?
just wondering lah, Prof boleh cuba ni raise the voice.
Sorry, I already raised my microphone.
Yang pelik.
Sekejap.
Itulah sampai saya kena pakai apa? Earphone.
Oh, betul lah, saya pun pakai earphone ni. Sekejap.
Thank
Ada
you, Prof.
masalah? Any others have a problem with my voice? Hello?
Ada saya okey je dengan suara doktor.
Okay. Saya cuba kuat kan? Okay, thank you. Okay. Okay, and then for the design stage, okay, so you need to know what is the important properties that you need to put inside your software, okay. So now, for example, we have here in our laboratory, computer lab, we have Plexis, okay, we have GeoStudio, okay, and then we have RockSign, okay. So before you use all this software, you need to know what is the input that you need to include, okay. So otherwise, whatever you put, definitely you may get whatever result, okay. So please be careful, okay, in terms of the properties that you put inside your software. Okay, so that's why laboratory test, soil investigation is very important, okay, before you construct or your design your any structure, okay. Okay, so for a geotechnical engineer or for a structure engineer, okay, this is the most two important things that should be considered, okay. So we need to make sure that in our design, okay, the building or the structure should able to provide a perfect serviceability, okay, and also prevent for any failure, okay. So for example, for the serviceability, we may discuss on SLS, serviceability limit state approach, okay. While for the failure, normally we discuss on the ultimate limit state approach, okay. So for example, logically, if we satisfied with the SLS, definitely we may prevent from the soil to collapse, okay. So however, if we did not satisfied with this SLS, most probably there will be no problems on the structure in terms of the structure will not fail, but we feel not comfortable to stay or to live inside what we call a building that have a lot of cracks, okay. I guess nobody in the world will buy a new house with a lot of cracks, okay. So that's why we need to make sure that both of these criteria should be considered and should be means that the designer should need to make sure that all both of these criteria are in a good place. Okay. So for example, serviceability it may related to settlement. Okay, tilted. Okay. So on our right side of the image is a Pisa Tower. Okay, which is located at Italy. Okay. So if you doesn't have any money, so you can go to Teluk Intan. Teluk Intan Tower. Okay. So I have visited the Teluk Intan Tower and I have a chance to climb up to the tower and then to clock to lock the clock because they're using what we call it, they're using uh, yeah they need to lock the clock, okay, in order to make sure that the clock is working. Okay, so yeah, you can go to the Teluk Intan if you doesn't have. Yeah, now we cannot go to Italy lah because we have a COVID. Okay, so yeah, on the left side of the picture is looks like is a failure of a collapse. Okay, collapse of a building. Okay, so we need to to measure the serviceability is more related to the settlement. Okay, so we need to make sure that the settlement, for example, for a single building or double story building, okay, so the settlement should not greater than 50 mm. Okay, so if the settlement is greater than 50 mm, okay, so we need to do some treatment, for example. Okay, and another thing, there will be a discussion on another discussion on what we call as on the angular deformation. Okay, which is the what we call as the building should not tilt more than 10 degree, okay, side by side. Okay, so there is another requirement when we want to design for a building. Okay, so for the failure, definitely we need to consider on the bearing capacity. Okay, so that's why we divide what we call as the calculation. Okay, up to factor safety of 3. Okay, so to prevent for any failure of the structure. Okay. Okay. So traditional soil mechanics and geotechnical engineering design was predominantly concerned with soil strength and stiffness, so that the design engineer could define the failure state of the soil or of control excessive deformations of the soil structure. Okay. So strength, okay, we can get from, for example, if we carry out carry out a triaxial test, okay, unconfined compressive strength, for example, a simple one. Okay, so we can get the strength of the material. Okay, so in order to get the stiffness, okay, so we may divide the strength with the strain. Okay, so means that what is the allowable strain, okay, before the soil start to fail. Okay, so that is the related to stiffness. Okay, so means that we need to make sure that the movement should not greater than what is the allowable stiffness, allowable strain. Okay, so for excessive deformations, okay, it, is it is it on? What does it mean? But with siapa tadi miss here? Is it on? Tak ada apa. Okay. Okay. So then why you cannot see my slide? Huh?
Assalamu alaikum, Professor. Actually, the slides we can see, but the first time I joined, the sound I could not hear, so I had to disconnect and join it again.
Okay.
Became okay. So now I think Mr. Rian Lim is texting that he cannot hear the sound, so I told him to just rejoin the meeting. So
Okay,
he
okay.
can,
Okay. So you need to rejoin. Okay. Might be that will help. Okay.
yeah.
Okay. Actually, I'm recording this lecture. Okay. So after the class, I will give the recorded file. Okay. So in this circumstance, the loading is considered static and the strain imposed within the saw may vary from about 10 power by minus 3, okay, in service to a few percent at failure. Okay. So when we discuss on the static, which is without any cyclic, okay, so the strain we call as an which is the value range from 10 power by negative 3, okay, to a few percent, okay. However, when we discuss on the cyclic, okay, the strain will be less than 10 power by negative 3, so we call it as a small strain, okay. So many circumstances where cyclic or dynamic loads are applied to the soil either by natural forces such as earthquake, okay. So we have here a problem of the earthquake, which is a natural force, which is from the ground or from the rock movement. Okay, then it trigger to it vibrate up to the ground. Okay, and then it reach to any building, nearby building. Okay, so then we have wind, water wave, or from man-made sources such as bomb blasts, traffic loads, and machine foundations. Okay. So for the natural, we have here earthquake, wind, and water wave. Okay. And for the man-made, we have bomb blast, okay, traffic loads, and machine foundation. Okay. So for instance, in UTM, actually we have a lot of quarry, rock quarry nearby. Okay. So they need to make sure that during their blasting, okay, the vibration should not less than certain value, which has been controlled by JMG, okay, Jabatan Mineralogi dan Galian, okay, Malaysia, okay. So that is the man-made source, okay. So I have an experience, okay, when the UTM team have been asked to monitor for the water treatment plant, okay, which is nearby in our area, Pulai Indah, okay. So we need to determine what is the cause, what was the cause of the crack, okay. So because the water treatment plant is not far from two or three, if one or two quarry nearby. Okay, so we install what we call it. We use an accelerometer, okay, to identify what will be the value of the vibration. Okay, at the end we come up. The cause is not from the blasting event. Okay, most probably is due to the uh, what cause of the ground movement. Okay, because the reservoir is located near to a sloping area. Okay, so the type of dynamic loading in soil or the foundation of structure depend on the nature of the source producing it. Okay, so the dynamic loads vary in their magnitudes, direction, or position with time. Okay, so we need to identify what will be the value, the magnitude, okay, where will be the direction, and at what time it will be arrived, okay, or at what time it normally arrive. Okay. So they have a several type of dynamic loads. Okay, we call as periodic load. Okay, it's a special type of load that varies in magnitude with time and repeats itself at regular interval. For example, operation of reciprocating or a rotary machine. Okay, so this is related to a machine. Okay, where they provide a vibration. Okay, in interval in several interval or regular interval. Okay, non-periodic loads are those loads that not show any periodicity. For example, wind loading on a building. Okay, but they still provide what we call as a dynamic loading. Okay, but it's not very sure okay, when the load will be the frequent of the loads. Okay, so we have a deterministic loads. Those loads that can be specified as the finite function of time, irrespective of whether the time variation is regular or irregular. For example, the harmonic load imposed by unbalanced rotating machines. Okay? So this is due to the problem with machines where they provide any harmonic loads. Okay, non-deterministic loads are those loads that cannot be described as the finite function of time because of their inherent uncertainty in their magnitudes and form of variation with time. For example, earthquake. Okay, so we cannot determine when actually the this type of load will become okay accurately, but the seismologists can estimate, but they cannot uh, they cannot predict accurately. Okay. So cyclic load are those load which exhibit a degree of regularity both in its magnitudes and frequency. Okay. So it's more related to how the loads have a tendency to there is no sound. Anyone have problem with this with the sound? Hello?
I'm okay.
Where do you stay? Ode, Ode, is it Ode your name? Yeah, because I give a lecture from UTM. So I guess there will be no problem in terms of internet connection from my rooms. Okay. Might be you have a problem. You have a problem with your own internet connection. Okay. So cyclic loads. Okay, and then we have the static. Okay, static is the normal loads. Okay, that we deal every day. Okay. We build a building that is the static loads. Okay, the building is actually the static load. Okay. So it may gradually over times, okay, which is the load. This is on static conditions. Okay, or with negligible dynamic effects. Okay, so this is an example of type of dynamic loads. Okay, so for the first one is a low speed rotary machine. Okay, so they have a certain cycle there. Okay, they show a sinusoidal type. Okay, for example, on for the left side, for the right side. Okay, here they show sinusoidal patterns. Okay, so and the thing we have here a simple impact of hammer and vertical acceleration due to pi driving. Okay, so this is effect for a pi driving. Okay, during the pi installations. Okay, so they drop a hammer and then the hammer uh, hit the top or the pi cap, the top of the pile, okay, the pi shoe. Okay, so then they produce this kind of signage. Okay, result. And the last one is the from the oscillogram of earthquake, okay, which is they measure in gravity, okay, which is show the pattern of the earthquake within 26 seconds, okay. So it means that all the cyclic loads is related to a cyclic loading under a certain period of times, okay. So compared to a static, it doesn't have any cycle, okay. So either it can gradual increase with a time, okay, or it will maintain on a certain value. Okay. So the magnitude of these dynamic loads are generally much smaller than most static loads and generate strain within the soil as low as 10 power by negative 6. Okay, it's very small strain. Okay, and in terms of the magnitudes, okay, we not compare for the earthquake. Okay, we just compare, for example, from machine, for example. Okay, so it's less than the normal static. Okay. Although the magnitude of these dynamic loads are often much smaller than static load, initial force may become important and must be considered in the geotechnical design. Okay, so yeah, the most important thing is to consider the initial force. Okay, so I will discuss later on the initial force. Okay, so we look on this diagram. So on the right side, okay, is the type of the loads, okay, either static or dynamic problems, okay, and the author lists all the type of the event, okay, and with the number of cycle, okay. So in terms of time, okay, so because temporary permanent is it be less than more than for a longer times, okay. So in terms of time for the dynamic, so it will happen in a very short periods, but it has a cycle, okay. And for the behavior in terms of shear strain, okay, so from a failure strain, large strain, medium, and for very small strain, okay. So in here they provide the shear behavior, okay. So for example, if the condition is less than negative power 10 power by negative 1, for example, okay, so we may collect all the information which is related to shear modulus and damping, and definitely if it's greater than 10 power by negative 1, okay, so we should use or collect all the information on the friction angle, for example, and cohesions, which is related to design for a static approach. Okay, so in this part, the author has listed all the related measurement methods, either in situ, which is at the site, and laboratory measurement, which is we get all the what we call as the undisturbed sample, and then carry out the measurement either by using wave propagation, which is Bender element, resonant column test, okay, monotonic or cyclic loading, okay. So actually in our geotechnical lab, so we have wave propagation, which is Bender element that could measure under a small strain, okay. And then we have a cyclic triaxial that could measure for the small strain up to large strain conditions, okay. So in the design for the what we call it for the cyclic loading, so we should have both of these parameter, which is the shear modulus, okay, and also the damping, okay. So this should be included in our analysis, okay. So I will discuss later on the shear modulus and also the damping, especially when we want to design for what we call as for the deep foundation, okay. Okay, so this is the initial, the tendency of an object to resist being moved, or if the object is moving, to resist a change in the speed or direction. Okay, so for example, this is a building, okay, and then suddenly they have the ground experience acceleration movement. So due to the building actually in the static condition, okay. So when there are movement on the ground, so this structure, okay, start to move, but before they start to move, they resist being moved, okay. Or if the object is moving, to resist a change in the speed or direction, okay. So simple analogy, okay. For example, if you are a passenger of a car, okay, suddenly the driver stop, brake the car suddenly. So okay, so suddenly, and then you may feel that you are moving forwards, okay. Okay, so that is the example of inertia. So Newton's first law say that the objects do not accelerate spontaneously. Okay, this property of matter which causes object to resist acceleration has been named as inertia. Okay, so Newton's first law is often called the law of inertia. Okay, so that is the definition of inertia. Okay, so most of the civil engineering structure involves some type of structure element which with direct contact with ground. Okay, so when we design a building, definitely the building we call as a superstructure. Okay, so beneath the ground there will be a substructure. Okay, so or normally called as a foundations. Okay, so when the external force such as earthquake act on this system, either the structural displacement or the ground displacement are dependent of each other. Okay, so means that when any earthquake event happen, okay, so this structure will start to displace, and definitely the ground should start first, okay, and start to displace at the ground level. Okay, so even though the foundation structure and the supporting soil are two different physical entities, they form a system, or in terms of the mechanics of behavior of such system, one component influences the behavior of the other, the end product being the result of this mutual action or interaction between the two. Okay, so due to this movement of the ground, okay, so there should be an interaction between the ground and also with the structure. Okay, so this is the essence of soil structure interaction. Okay, so now we have some understanding on the soil structure interaction, or they call as SSI. Okay, soil structure interaction. Okay, due to the movement of the ground, okay, from the earthquake event, so this movement will start to shake the building. Okay, so then or to vibrate the building, so then there will be an interaction between soil and structure. Okay, so the process in which the response of this soil influence the motion of the structure, and the motion of the structure influence the response of the soil, is termed as soil structure interaction. Okay, conventional structure design method neglect the SSI effects. Neglecting SSI is reasonable for large structure in relatively stiff soil such as low-rise building and simple rigid retaining wall. Okay. So in our common design or structure conventional design, okay, normally we not include what we call as the SSI approach, okay, or SSI effects, okay, especially when we design for a light structure or uh, low rise building, okay. And yeah, in here they mention also on the stiff soil, okay. So for example, if it is stiff soil or dense soil, so there will be no problems, okay, if we design it without the SSI, okay, effects. Okay, the effect of SSI, however, become predominant for heavy structure resting on relatively soft soil, for example, nuclear power plant, high-rise building, and elevated highway on soft soil. Okay, so there will be two things here. First, if the structure is very big, okay, or high, okay, it's very high, okay, and a sensitive, what we call as a sensitive structure, nuclear power plant, we not allowed for this for the what we call it for the power plant or for the structure to have any cracks, okay, because it may allow for the nuclear, yeah, contamination problems. And the second thing is the ground itself. It consists of soft soil, okay, or a loose soil when we deal with a sand material, okay. So if we have a problem with the soil itself, okay, so we need to consider the effect of the SSI, especially for the area that within within the common earthquake area, okay. However, I think in Malaysia we are not within the region that normally earthquake happen. Okay. So, however, currently, especially on bridge design, okay, the authority require for the designer to include the effect of the vibration, okay, due to the earthquake. Okay. Okay. So damage sustained in recent earthquake such as the 1995 Kobe earthquake have also highlighted that the seismic behavior of a structure is highly influenced not only by the response of the superstructure but also by the response of the foundation and the ground as well. Okay. Based on this explanation, means that during the Kobe 1995 earthquake, so they have noticed that the important to integrate the effect or the interaction between soil and the structure, okay, in the design, okay, in order to reduce the failure of the building. Okay, here's the modern seismic design code, such as standard specification for concrete structures, seismic performance verification JSCE 2005 stipulate that the response analysis should be conducted by taking into consideration a whole structure system including superstructure, foundation and ground. Okay, so they come up with a well, with a wise conclusion, which is they propose to have a seismic design code, okay, which is consider this SSI effects. Okay, so the process in which the response of the soil influence the motion of the structure and the motion of the structure influence the response of the soil is termed as SSI, okay, soil structure interaction. Okay. So stiffness relate increment of stress, increment of strain. Okay. A knowledge of soil stiffness is required to calculate ground movement and to obtain solution to problem of soil structure interaction such as loads on retaining wall. Okay, so this is just an example. Okay, all of the structure is important, not only on this retaining wall structure only. Okay, so if I guess most of you have as an experience using a commercial software, especially for geotechnic, for using the Plaxis. Okay, so we need to include all the information on the strength, stiffness. Okay, when we want to use or run for any analysis. Okay, so if you choose to run for a seismic, okay, so we need to include the shear modulus or damping ratio value in the design. Okay, so this an example when we discuss on the SSI. Okay, so when an earthquake occurs, the building and the ground vibrate with influencing each other. Okay, so this is the earthquake wave. Okay, from certain epicenter. Okay, so it start to move. Okay, to the ground, to the soil, and then it will interact to the pile or to the foundation, and then transmit to the top of the building. Okay, that's why when I did my PhD in UK, okay, there are one guy from Thailand. Okay, so he study on the effect of shredded tire. Okay, to reduce the effect from the vibration. Okay? So they mix the soil or have a layer of shredded tire. Okay, so this shredded tire will be act as a damping system. Okay, so for example, if we treat well the soil, so the wave would not is the magnitude of the wave will be reduced. Okay, before the wave start to transmit to the structure. Okay, so means that if we treat well the soil, okay, so we could reduce uh, the reduce the the cost, okay, for the foundation to fill. Okay, so this phenomenon is called dynamic soil structure interaction, and is recognized as being very important for seismic design of structure. Okay, so when we discuss on the soil structure interaction, okay, they definitely the most important structure is the substructure itself. Okay, because the source of the vibration is from the soil, and the soil we transmit to the substructure, and later on we goes up to the main building or superstructure. Okay, so role of foundation under a static condition or a normal condition, supporting the dead weight and the life load of the building, transmitting this load to the ground. Okay, so yeah, from the load, from the slab to the beam, to the column, and to the foundations. Okay, so that is the role of the foundation. Okay, so during the earthquake, transmitting the ground motion to the building. Okay, bearing the building vibration, transmit them to the ground. Okay, so it means that yeah, when the source of the earthquake is beneath the foundation, so it will transmit the ground motion to the building. Okay, and then it bear the building vibration. Okay, and then transmit them to the building. Okay, because the earthquake is in a wave or in a cyclic loading, so it means it can transmit from the ground, okay, to the top of the building via the foundations. Okay, the ground and the building influence each other through the foundation, and it's called, okay, dynamic soil structure interaction. Okay, So the degree of the influence of SSI on response of building depends on stiffness of the ground. Okay, so the stiffness is much more related to the property of the ground itself. Okay, so for example, if a loose sand, so compared to a dense sand, okay, so definitely the loose sand is weaker compared to the dense sand or the dense material. Okay, so dynamic characteristic of building itself, that is natural period, damping factor. Okay, so for the building, okay, for the foundation as well. Okay, so it depends on its natural period or natural frequency. Okay, for each structure, they have their own natural frequency. Okay, so it means that if the natural frequency, if the vibration is greater than natural frequency, so it has a potential for the structure to fail. Okay, so and as well they have their own damping factor. Okay, which is something that could reduce the effect from the earthquake vibration. Okay, so if you have a chance, you can go to Japan. You can go to Japan and then you can see a building with a lot of what we call a damping system. Okay, so I used to visit, to visit Nagoya, for example, Hokkaido. Okay, so I saw a lot of damping system that they built in their building. Okay, to resist or to reduce the effect from the earthquake. Okay, and the last one is the foundation types. Okay, so in here I have list several type of foundation, which is the spread foundation or a shallow foundation, normal foundation. Okay, then we have a pile foundation without basement. Okay, and then they have a basement without pile. Okay, and the last one is basement with pile. Okay, so it means that the type of the foundation also reflect to the response of the SSI. Okay, okay, the position where the SSI take place. Okay, through the bottom surface of the foundation. Okay, which is the A. Okay, so it means that through this bottom. Okay, through the pile foundation. Okay, so the SSI will take okay here, and bottom surface and the side wall. Okay, so starting from here. Okay, the bottom and the side. Okay, and the last one through the basement surface and the pile. Okay, this basement surface. Okay, and also the pile. So this is combination of pile and basement. Okay, so this is the contact between the ground between the ground with the structure. The influence of SSI become remarkable and more complicated as the amount of contact between the ground and the foundation increase sequentially in order from A to D. Okay, so the A is less complicated and the D is the most complicated. Okay, in terms of analysis or calculations. Okay. Okay, so this is an example where a building, okay, experience an earthquake or vibration from the earthquake. Okay, so in here we have a earthquake fault. Okay, so the interaction between ground and okay, when the seismic wave, which is the note as a E naught, generated by the earthquake fault, reach the bottom of the foundation. Okay, so when it reach the bottom of the foundation, okay, they divide into two types. Okay, the wave E1 entering into the building. Okay, so that is the E1, and the wave of F0 being reflected back into the ground. Okay, so there will be E1 and there will be F0. Okay, so the wave E1 is called the transmission wave, while the wave F1 is called the reflective wave. Okay, So how to measure this kind of wave? Okay, from the earthquake fault, okay, we can use a seismograph. Okay, for the E type, we can use the accelerometer. Okay, so for example, if you plan to monitor what we call as the health, okay, they are one topic called structure health monitoring. Okay, so you want to measure the health of the building, so you may include all the sensor. Okay, for example, install on the building and accelerometer. Okay, and on the ground install the seismograph. Okay, so you can measure uh, what will be the cost after the earthquake or any vibration effect. Okay, because I plan to have this kind of system, to build this kind of system. Okay, uh, but not consider as earthquake event, might be from any vibration due to the machine or due to the quarry effect, blasting. Okay, so if we install, and then we can provide a very good assessment of the building condition. Okay. Then the transmission wave entering into the building travel towards the top of the building with subjecting the building to vibration. Okay. So then E1 will move up to the top. Okay. And then they will reflect as a F1. Then they reflect at the top and travel back down to the foundation. Here a crucial phenomenon occur for consideration of the SSI. Okay. So when they move top, then they go down again. Okay. So they have two type of effect, which is F2 and R1. Okay. So when the wave that are reflected at the top of the building and traveling down, F1, traveling downward, F1, reach the foundation, a part of them is transmitted into the ground, while the rest is reflected back again and one start to move outward through the building. Okay, so this phenomenon will continue until the magnitude of the wave will reduce. Okay, at we reduce after certain cycle. Okay, so the former wave escaping into the ground are called as radiation wave, which is the R1. Okay, so when the amount of this radiation wave are small, the seismic wave once transmitted into the building and the building continue to vibrate for a long time, the apparent vibration condition become the same of the small damping of the building. Okay, the damping caused by the escape of the seismic wave, which has been transmitted into the building into the ground, is called radiation damping. Okay. So means that the building also have a the building have a damping system. Okay. So if we can improve the damping system in the building, so we can reduce the number of the vibration. Okay. So when the building foundation is forced to vibrate vertically, a stress called contact earth pressure is caused at the boundary between the bottom surface of the foundation and the ground. Okay. So this is related on the contact earth pressure. Okay. So there will be three types of contact earth pressure, which is the distribution of this contact earth pressure over the bottom surface of the foundation is called the contact earth pressure distribution. Three types of distribution where we have here a rigid foundation, okay, uniform soil classification, and parabolic distribution, non-linearity are observed. Okay. So it depends on the type of the material, okay, and also the type of the loading. Okay. So for example, if rigid, normally we discuss on what we call it as a normal or a uh, static loads. Okay. So we have a uniform loads. Okay, and then we have a parabolic distribution, which is normally related to a material of loose material. Okay, so this is the type of the contact earth pressure. Okay, for foundation and substructure solution with an increased complexity, more involved method of calculating the force within and displacement of the structure elements are required. Okay, the use of the more basic approach that rely heavily on hand calculation or rule of thumb may not be appropriate in such situation, as there may be too many degrees of indeterminacy within the problem, or they may simply be too time consuming to use. Okay, so as a result, the use of finite element model allowed the user to create soil structure model of the whole or part of the problem with relative easy. Okay, so when I did a reading on this soil dynamic, okay, yeah, for example, if they still does not have a very comprehensive formula, okay, to estimate, for example, for a bearing capacity for a shallow foundation, and the author just rely on the previous laboratory work, okay, in order to calculate for instance for a bearing capacity for a shallow foundation. Okay, so as a result, most of the calculation, or what we call a hand calculation, okay, if we discuss on the hand calculation, most of the hand calculations for the dynamic loads is still rely on the static approach. Okay, I will discuss later on when we go for example, for the shallow foundation and also on the lateral stress. Okay, so they still rely on what we call as on the static approach. Okay, so if we want to go for a very extensive analysis, so we need to use the finite element model. Okay, same like we discussed on the slope stability analysis. Okay, so we understand how to use the Bishop, the Terzaghi, the Meyerhof, okay, uh, which is on the method of slices. Okay, so at the end, all the reference book suggested to use the commercial software, okay, to analyze the problems. Okay, due to its complexity, okay, and due to time consuming. Okay. Okay. This model can be generally then be modified to respond to changes in the design or undertake parametric study that might be otherwise take a great deal of time. Okay, so again, okay, when we want to, for example, carry out for a parametric study, for example, we want to differentiate or vary the soil condition or the structure geometry. So the author suggested need to use the finite element method or software. So soil structure model can also provide us with a means of predicting the impact of the one structure on another. Displacement and stress changes can be calculated for different construction phases. Okay. So, but the important thing is to include what we call as the shear modulus and damping uh, value for the soil properties under a cyclic loading. Okay. Okay. Then we move to wave propagation in soil. Okay. So we may identify we need to identify what is the pattern or what is the wave, okay, that propagated in the soil. Okay. In here, I have classified three type of wave. Okay. which is related to the soil, okay, or ground itself. Okay. For soil, three types of wave are readily encountered and are of importance. Okay. The first two are terms body wave, which are propagated within the soil and comprise the compressional wave and shear wave. Okay, so they have two type of wave. Okay, on the body of the inside the soil. Okay, they call as a body wave. Okay, so they have a two type of wave, which is P wave and S wave. Okay. So what is the importance of this wave? Okay, so we can get the value of the what we call as the shear modulus. Okay, so from either P wave or S wave. Okay, because the shear modulus will be used. Okay, once we want to carry out for the analysis. Okay, and at the same time we can get determine what we call the layer of the material. Okay, the type the condition of the soil. Okay, by using this S or P wave. Okay, if you are familiar with seismic or resistivity, okay, so uh, both of the material use they use the wave, okay, to measure the thickness of or the layer of the soil beneath the ground. Okay, so in relatively soft saturated near surface sediment, which is likely to be the case for a large number of geotechnical problems, the P wave is dominated by the bulk modulus, okay, of the pore fluid, which is the water is hard compared to the soil. Okay, this is case for a saturated where the soil has been filled by the water. Okay, so P wave is better. Okay, when we want to measure or we want to get the information of the soil by using the P wave if we deal with fully saturated soil. Okay, and the resultant VP may be close to that of the pore fluid. Okay, if the soil is unsaturated, okay, the P wave can reach from that of the soil metric without no pore fluid to that for the saturated case. Okay, so that is the problem with the P wave when we use to under an unsaturated soil. So I mean that unsaturated soil, the soil have the pore of the soil is not been fully filled by water. Might be they have air, okay, air trapped inside the pore. Therefore, the use of VP to determine the property of the soil is problematic. Okay, so it's not suggested to use the shear wave. Okay, P wave. However, pore fluid do not carry shear stress, so the velocity of S wave is only influenced by the soil and not by the pore fluid. Okay, so it can also be shown that during most dynamic loading event, it is cyclic changes in the shear stress that influence the behavior of the soil. Okay, so in here we notice that uh, the the pore fluid do not carry shear stress. Okay, because the water could not be shear, the water can be compressed. Okay, so that's why the water doesn't have any CN5 value. Okay, sorry, any phi value. Okay. So it can also be shown that during most dynamic loading, it cycle changes in the shear strength that influence the behavior of the soil. From the theory of propagating wave, it can be shown that the wave velocity through the soil is related to the stiffness of the soil. Okay, by using equation number 1. Okay, so this is the stiffness for the soil. Okay, and the shear modulus. Okay, which is the characteristic of the soil stiffness. Then rho is the soil density. Okay. So when we multiply the what we call as the S wave power by 2 with the rho, so we can get the value for the shear modulus. Okay. Okay. So it's very yeah, impossible to get what we call as the sample and then carry out for the testing at the lab. Okay. So on the other hand, we may use what we call as seismic or resistivity. Okay, and then we get all the information based on the especially on the seismic by using the P wave, S wave. Therefore, changes in Vs within the soil can be used to determine the small strain stiffness, and the measurement of S wave is commonly employed to determine the dynamic behavior of the soil at small strain. Okay. So this is the diagram for the P and the S wave. Okay, where the P is represent the compression wave, S is the shearing wave. Okay, so shear wave, a wave in which the disturbance in an elastic deformation perpendicular to direction of the motion wave, and compressive wave, a wave in which the disturbance is compression of the mediums. Okay, so the last one or the third is the relic wave. Okay, which travel along the ground surface. Okay, relic wave measurement have gained in important in recent years since ground surface measurement can be readily and easily undertaken without the need for any intrusive investigation. So it means that the relic wave they measure on the ground surface, okay, not inside what we call it inside the ground itself, such as those required for measuring P or S wave. There is no direct link between the velocity of relic wave and the soil stiffness. However, it has been shown that for nearly all value of Poisson ratio, okay, that is the if the Poisson ratio is same, so Vs approximately equal to 1.09 VR. Okay, so if we obtain the VR, so we can get the Vs, then later on calculate for the G. Therefore, measurement of relic wave can give a good determination of shear wave velocity from which G can be derived. Okay, so in here we have three types of wave that propagated inside the soil. Okay, so this example of the relic wave, which is have a slightly similar with the what we call as the S wave, but it's only measure on the ground surface. Okay. Can we have 5 minutes breaks? Okay, so we continue at 3:30. Okay, I guess I have only have 30 minutes to finish this slide, and then we try to finish before 4. Okay.
تلویزیون زده مش نیم صدای هیچ کس نمیشنم.
I'm also lost the professor sound. Maybe the mic is off.
صحیح شد. I got it. Thank you.
كده أستاذ گفت به خاطر وقفه و یا
گفته بخیر اون دیگه یکی دیگه جواب داده که اوکی دکتر با هم مایکش بند نزده. کلا خدا بیزنه خامم.
So then I will continue on methods, okay, to overcome or to reduce the problem due to the vibration of the earthquake. Okay. So for this particular topic, okay, I may discuss on stabilization of the ground for geotechnical structure. Okay. So in both seismically active and inactive area, soil improvement technique are commonly used as a sites where the existing soil conditions are expected to lead to unsatisfactory performance. Okay. So yeah, for example, if you want to improve a land, okay, to construct uh, a building, okay, uh, yeah, if there are no if earthquake event, so we still require to uh, improve improve the soil engineering properties of the land. Okay, so and it can more be important, okay, when the area is within the region of an earthquake, okay, but this method is only applicable, okay, when we want to develop a new area, okay. The existing area is not, if the land has been developed, so it's not uh, practical to use this kind of approach, okay. So unsatisfactory performance can be take many form, but usually involve unacceptably large soil movement, okay. The movement may include horizontal or vertical or both components and may take place during or after earthquake shaking. Okay, in the absence of the earthquake shaking, unacceptable movement usually result from insufficient soil strength or stiffness. Okay, so strength and stiffness is relatively related. Okay, uh, to reduce the shaking from the earthquake. Okay. Consequently, most soil improvement were developed to increase the strength and stiffness of the soil deposit. Okay, during the earthquake, the build-up of excess pore pressure can lead to very large deformation. Okay, so yeah, due to the ground experience a vibration. Okay, so the water inside the soil, okay, we start to going up, okay, and then it can make the condition become worse, okay. Yeah, for example, yeah, the simple analogy that we can have here, okay, if you pour, for example, a sugar inside a container, okay, in order for you to make sure that you want to fill more volume, so you need to shake the bottle, okay, and then the soil will become the sugar will become more dense, okay, then you can fill and add on more sugar on the top of the existing sugar, okay. So the same goes to the soil, okay. So when they experience any shaking, okay, so the water inside the soil, okay, will start to moving out, okay, from the soil, from the soil, okay, and it will mix together and it will behave as a liquid later on. So that's why we have a term of liquefaction, okay. So if you have a time, you can Google inside uh, inside the Google, or you can look on the YouTube. You type soil liquefaction, okay, you can see that there are a lot of event where the soil behave like a water, okay. So the most common soil improvement technique can be divided into four major category, okay: densification technique, reinforcement technique, grouting and mixing techniques, and drainage technique. Okay, so this is four major types of ground improvement, okay, that can be used to overcome or to reduce the effect from the earthquake. Okay, so we go first for the densification technique. The particle that comprise a particular soil can be arranged in many different ways. The strength and stiffness of the soil is higher than the particles are packed in a dense configuration that when they packed loosely. Okay, so there is there is a what we call a common basic understanding. Okay, So the strength and the stiffness is higher when we have a dense material compared to the loose material. Also, the tendency to generate positive excess pore pressure due to cyclic loading is lower than the soil is dense than when it is loose. Okay? So when the soil is dense, so definitely there are no pore, okay, inside the number of the pore is less compared to the soil with that it is in a loose condition. So it may not provide a space for the water to move, okay, compared to the loose condition. As a result, desertification is one of the most effective and commonly used means of improving soil characteristics for mitigation of seismic hazard. Okay, so the most common approach to desertification includes vibro techniques, dynamic compaction, blasting, and compaction grouting. Okay, so this is the type which is common method used, okay, in practical. Okay, so in here we have a vibro techniques. Okay, so vibro technique use probes that are vibrated through a soil deposit in the grid pattern to densify the soil over the entire thickness of the deposit. Okay, the vibro technique can divide into those based on horizontal vibration, which is called as a vibro flotation, and those based on vertical vibration, which is called as a vibro root systems. Okay, first is horizontal, second is vertical. Okay, vibro technique are among the most commonly used technique for mitigation of the seismic hazard. Okay, so this is the methods commonly being used. Okay, where uh, where at the tip of the hammer or the device, okay, they could provide a vibration. Okay, or if you have any experience uh, when some of you have uh, did your what we call practical training. Okay, what we call during day one to during the concreting process. Okay, they use a vibrator to make sure that they could overcome the honeycombs problems. Okay, so they vibrate inside the soil will become dense. Okay, so they need to arrange in a grid pattern. Okay, okay, so this is dynamic compaction. Okay, so as we can see in here, there are a crane. Okay, where the crane pull what we call as a plate, steel plate. Okay, put a steel plate up to 30 meter and release. Okay, down to the ground. Okay, where the weight of the plate is about 6 to 30 tons. Okay, so they arrange in the grid pattern. Okay, so later on they will compact or trim the platform to become flat or smooth. Okay, so dynamics is performed by repeatedly dropping a heavy weight in a grid pattern on the ground surface. Okay, so definitely the ground will be compacted well. Okay, by using this kind of methods. Okay, another one is the blasting methods. Okay, where they install uh explosive. Okay, uh inside the soil. Okay, with a grid pattern arrangement. Okay, before they before they put the explosive, so they need to bore a hole. Okay, up to 15 meter, and then uh, after they complete the detonation, so they backfill again the area. Okay, to be used for the construction purpose. Okay, so this is type of one the improvement ground improvement method by using the plastic. Okay. So compaction is by injecting what we call as a cement or any hardened agent in which is in a liquid form. Okay. So they inject. Okay. So this material will start to harden, and then later on it become a part of the ground. Okay. So in some cases, it is possible to improve the strength and the stiffness of the existing soil deposit by installing discrete inclusion. Okay, so they include something inside the soil. Okay, either by using a piling system. Okay, to ensure that the density of the area getting better. Okay, so this is a common type of inclusion method, which is a soil stone column. Okay, so they bore a hole. Okay, and then they feed the hole with the stone. Okay, at the same time they do a vibration process. Okay, to make sure that the stone has been filled up, filled inside the hole uh, in a very good arrangement. Okay. This is a compaction pile. Okay, they install a series of pile inside the soil. Okay, so yeah, definitely when we introduce some element, a stiff element inside the soil, so the stiffness of the material, the stiffness of the whole material will become higher. Okay, compaction pile are displacement pile, usually precast concrete or timber that are driven into a sand or gravel deposit in the grid pattern and left there as a permanent structure. Okay, compaction pipe improve the seismic performance of a soil deposit by three different mechanisms. The flexural strength of the pipe themselves provide resistance to the soil movement. The vibration and displacement produced by their installation cause densification. Okay, the installation process increase the lateral stress in the surrounding the pile. Okay, so the material itself, the installation itself provide resistance to soil movement. Okay, during the installation, the vibration due to the installation can cause uh, the soil to become more dense. Okay, and the material itself, the piling structure, the pile structure itself would increase the lateral stress. Okay, because the pile with a very long uh, length, okay, could provide an additional higher lateral stress. Okay, the engineering characteristic of many soil deposit can be improved by injecting or mixing okay cementitious material into the soil. Okay, so they call uh, they call this type of method is a deep mixing methods. Okay, so where they mix a soil with a stabilization agent, okay, which is for example cement or lime. Okay, under a certain required depth. Okay, so they're using a special mixer. Okay, where the mixer at the end of the mixer they have a special nozzle which is could inject uh, the stabilization agent either in dry or wet condition. Okay. So this is a type of grouting, okay, where I have discussed previously. Okay, so this is the deep mixing methods. Okay. So this is the machines equipped with mixing blade. Okay. So they start to mix, and during the mixing process, okay, they pour or they inject the stabilizer, okay, and then it should be mixed well with the with the soil, okay. So this is the procedure, okay, until they construct a pavement on the top of the uh, im- improvement ground. Okay. Actually, when I did my PhD, so uh, I'm I did my study on this deep mixing method, okay, by using a small scale physical modeling instruments. Okay. So the last one is the drainage technique. Okay. So as we know that the water is the main problems, okay, that could reduce the strength and the stiffness of the soil. Okay. So in order to increase the stability or the strength of the soil, so we need to uh, dewatering the water from or pump out the water from the soil. Okay. So this is what we call as a prefabricated vertical drain. Okay. So it can accelerate the consolidation process, and it also can make the soil become more denser. Okay. So for example, when they install this kind of prefabricated vertical drain, so it should be integrated with the surcharge method. Okay. It could not only rely on the PVD itself, because the PVD only to provide a drainage system. Okay. So the water still trapped in this ground, okay, without uh, uh, without uh, without apply a surcharge on the top uh, of the ground that has been installed by the PVD. Okay, so the use of the loading is to press the press the soil. Okay, and then which is to add an additional load. Okay, which is provide pressure. So from there, the water will start to move out from the soil by uh, from by from the PVD columns. Okay, so it means that we need to have a surcharge plus PVD, not only PVD. So if we use only PVD, so the method is not efficient, okay, or not working well. Okay, so I guess that that's all for today. Okay, so uh yeah, um if you have any problems, okay, so we can communicate by using the WhatsApp groups. Okay, and I will share my recorded uh lecture, okay, with you once I have received the feedback from the webback. Okay, because I save it in the cloud. Okay, so for that I end my class. Okay, and then we will meet next 2 weeks. Okay, next week is Prof Ramli class. Okay, okay, thanks, and then with that I end my class. Okay, Assalamualaikum warahmatullahi wabarakatuh and good afternoon.
Thank you, Doctor.
Thank you, Doctor.